In this session, we're going to see how to graph rational functions. This is where the things that we have seen about rational functions will come together. For our first example, we are told to analyze and graph a function h of x is equal to negative 2 over x plus 1. And in this context, analyze means to find the domain, intercepts, and asymptotes. As you should recall, the domain is going to come from problems in the denominator, or it's going to be indicated by problems in the denominator. And in this case, the domain is going to be the set of x such that x does not equal negative 1, right? The value that zeroes out the denominator. Because this is a reduced rational expression, we have a vertical asymptote of x is equal to negative 1. And in this session, we're going to see how that indicates the graph or the shape of it. The degree of the numerator is 0. The degree of the denominator is 1. Therefore, we have a horizontal asymptote of y is equal to 0. Remember, that happens whenever the degree of the numerator is smaller than the degree of the denominator. Now for the intercepts, the x-intercept would be the value that makes the fraction equal to 0. There is no such value because the numerator is negative 2. In other words, we would set the numerator equal to 0, but negative 2 equals 0 has no solution, and so there is no x-intercept. For the y-intercept, we are going to evaluate h of 0, and we can see that the y-intercept is going to be 0, negative 2. Now, let's get some axes and put this together and draw a graph. Okay, so we said in the previous video that asymptotes are lines that govern the behavior of a graph. So we have a vertical asymptote of x equals negative 1. What that means is we're going to draw a dotted vertical line at x equals negative 1. We have a horizontal asymptote of y equals 0, which means we're going to put a dotted line along the x-axis where y equals 0. Those are just going to be guidelines for our graph, and we'll see how we use those in just a minute. The y-intercept is 0, negative 2, and so I'm going to put a dot at 0, negative 2 on the y-axis. There is no x-intercept. We're all fine and good there. Now, if we used a table of values using inputs and outputs, we could crank out some numbers, and I encourage you to do so. And if you did, what you would find is that the graph kind of hugs the asymptotes. You see, that's what I mean when I say the asymptotes govern the behavior of a graph. An asymptote is a line that the graph would try to be if it could. And so what we end up with is a branch to the lower right and a branch to the upper left, and both of the branches display this asymptotic behavior. If this graph seems reminiscent of the reciprocal function, there's a good reason for that. You see here our h of x, which is negative 2 over x plus 1, is the reciprocal function that has a scaling factor because of the 2. It's upside down because of the negative, and it's been moved to the left by 1 unit. And so this is the picture that we have. Now, since analyze said find the domain, intercepts, and asymptotes, I'm going to go ahead and circle all of that information. It's all reflected in my graph. And we're going to look at the next example. Next, same instructions. Our function is f of x is equal to 2x squared plus x minus 8 over x squared minus 4. First thing I'm going to do is factor the denominator into x plus 2 times x minus 2. That gives us our domain, which is the set of x such that x does not equal plus or minus 2. And since the numerator does not factor, that also gives us our vertical asymptotes of x equals 2 and x equals negative 2. The degree of the numerator is 2. The degree of the denominator is 2. And since those degrees match, we're looking at the ratio of leading coefficients, which, if you like, is 2 over 1. And remember, when the degrees match, we have a horizontal asymptote. that horizontal asymptote has the equation y equals the ratio of leading coefficients, and so in this case y equals 2. For our x-intercepts, we look for values that make the fraction equal to 0. Remember, an x-intercept is where y is equal to 0. Y equals 0 means that f of x is equal to 0, and the only thing that can make a fraction equal to 0 is its numerator. So up here I'm going to write down what would happen if the numerator were to equal 0. 2x squared plus x minus 8 is equal to 0. This is a quadratic equation which I can solve using the quadratic formula. When I do that, I get x equals -1 plus or minus the square root of 65 over 4. So making space for my ordered pairs, my x-intercepts are -1 plus or minus the square root of 65 over 4, comma 0. Since I'm going to be plotting these, I'd like to get a decimal approximation, and so my calculator tells me that the approximate x-intercept points are 1.80 and 2.30. The y-intercept, remember, is where x is equal to 0, and that means we're looking at f of 0. In this case, we have a y-intercept of 0, 2. Let's go ahead and put this stuff down in our graph. I'm going to draw the vertical asymptotes, the horizontal asymptote. I'm going to plot the x-intercepts and the y-intercept, and then we'll see where we stand. Okay, I had to kind of ballpark it on those x-intercepts, and you can do the same as long as what you put down is reasonably close to what it's supposed to be. Now to draw the graph. I know that the graph is going to connect the y-intercept at 0, 2 with the x-intercept at about 1.80. From there, though, I don't know, does it go bounce up off of the axis and become asymptotic up there? Or does it maybe just keep going all the way down? It's going to be the latter, and we'll see how we can figure that out in just a minute. To the left of that y-intercept, we again have choices. It could bounce down and be asymptotic there, or it could go kind of up and look maybe like a cubic type of graph. It's actually going to be the latter, and again, I can tell you why. If it were the case that it was supposed to bounce down, then we would pick up another x-intercept, which doesn't exist. You see, we already found all of the x-intercepts that are in this graph. So the graph cannot cross the x-axis anywhere other than those x-intercepts, which means the graph must point up. So let me clean up this mess. Now let's turn our attention to the other x-intercept, -2.3, 0. The graph needs to go through that point, and I see this asymptote down here, so I'm going to draw it so it's asymptotic. And then it's going to curve and become asymptotic with the line y equals 2. I also know that to the right of all of this, the graph cannot come from the bottom and cross the x-axis and become asymptotic, because that would be another x-intercept that we didn't have. And so it actually needs to be a branch in the upper right portion that is asymptotic with our two asymptotes. How do I know that the graph doesn't cross the asymptote, say, to the right of 5 or to the left of -5? There's a pretty large contingent of people out there who hold that horizontal asymptotes cannot be crossed, and they're all wrong. Check it out. We have this horizontal asymptote being crossed at the y-intercept. The deal is that a horizontal asymptote cannot be crossed when x gets really big and when x gets really small. A horizontal asymptote can be crossed near the origin. A vertical asymptote will never be crossed, because those are forbidden x values, remember. And so as part of the analysis of a graph, it's usually a good idea to find out, does it cross the horizontal asymptote? And to find that out, what I need to do is set the expression that defines the function equal to the value of the asymptote, and see, does y ever equal, in this case, 2. the expression 2x squared plus x minus 8 over x squared minus 4 is from the function, but then the horizontal asymptote was y equals 2, so we want to know if the function ever equals 2. Well, this is a rational equation. I'm going to solve it by clearing the fraction. We get 2x squared plus x minus 8 is equal to 2x squared minus 8. And the 2x squared subtract out. When I add 8 to both sides, we get x is equal to 0. And so the function value is the same as the asymptote value when x is equal to 0. In other words, the graph crosses the horizontal asymptote when x is equal to 0. And since that was the only solution, that's how I knew at the beginning that the graph didn't go up and become asymptotic that way, and it had to go down from that x-intercept. And that's also how I know that the asymptote is not crossed on the sides to the right and to the left of 5 and negative 5 respectively. Well, let me circle the fruit of our analysis because we were supposed to find all that. Might as well advertise it. And there we are. Next, same instructions. R of x is equal to x squared minus 4x minus 5 over x minus 3 is our function. I'm going to write this in factored form. R of x is equal to x minus 5 times x plus 1 in the numerator and then x minus 3 in the denominator. And what I want you to do is perform the analysis of this function as best you can. So go ahead and pause the video, work on that. Okay, let's work our way through this. Because the denominator is x minus 3, I know the domain is the set of x such that x does not equal 3. Nothing reduces. That gives us a vertical asymptote of x is equal to 3. As I look at the numerator, it's degree 2. As I look at the denominator, it's degree 1. And this means we're going to be looking at a slant asymptote or an oblique asymptote, you know, whichever one you want to call it, I really don't care. But we're going to get that from long division. And so let's set up some long division and see how that turns out. And we have a quotient of x minus 1. So that's going to be a slant asymptote y equals x minus 1. Remember, we don't include the remainder in that consideration. So let's scroll back up and write that down. X-intercepts are, of course, values that make the numerator equal to 0. And so 5, 0, and negative 1, 0. And the y-intercept is what happens when we evaluate the function at 0. And so the y-intercept is going to be 0, 5/3. And then there's one last thing I want to know. Does the graph of the function ever cross the slant asymptote? So as before, what we're going to do is we're going to set the expression equal to the slant asymptote to find out if there are any values where they coincide. So let's do that down here. So again, I'm taking the expression that defines the function x squared minus 4x minus 5 over x minus 3, and I'm setting it equal to the expression that gives us the slant asymptote to find out if there's an x value where those two agree. We're going to clear the fraction and then solve the resulting equation. Clearing the fraction and then foiling gives me x squared minus 4x minus 5 is equal to x squared minus 4x plus 3. Subtracting x squared from both sides, adding 4x to both sides, I get the negative 5 is equal to 3. And that's not true. This equation has no solution. Now we have a meaning for what it means to have no solution. In this case, it means that the function and the asymptote do not intersect. So let's put this stuff together. I already have it in yellow, this slant asymptote. Might as well start drawing that. So y equals x minus 1 has a slope of 1 and a y-intercept of 0, negative 1. And then we have our vertical asymptote of x equals 3. I'll go ahead and get that down here. And I draw those dashed because they aren't actually part of the graph. They inform the graph, but they aren't part of it. We have, let's see here, x-intercepts of 5, 0 and negative 1, 0. And a y-intercept of 0, 5/3. That's like 1 2/3. And now we're ready to go. So we need a graph that's going to obey the asymptotes, not cross any of them. Again, vertical asymptotes are never crossed. horizontal or slant asymptotes, we can figure out if they get crossed, but in this case the answer was no. And we have these intercepts that we're looking at. Suppose I want to know how the graph is going to go with this x-intercept of 5, 0. What I can do is, if I need to, set up an xy table, put in some values, crank out some values. And if you did that, then you would find that we have a branch that hugs the slant asymptote, comes down through the point 5, 0, and then hugs the vertical asymptote on its way down. So again, the asymptotes help us figure out how to draw the graph. To the left of that vertical asymptote, we're going to come down from the top, behaving asymptotically, come through the y-intercept and then the x-intercept, and then it becomes asymptotic, which means it's trying to be that slant asymptote's line. It'll just never achieve it. Let's go ahead and be proud of the intercepts, asymptotes, and domain that we found because we were told to find all that stuff. And there we go. Next, we're going to look at the function r of x is equal to 5 times the quantity of x squared minus x minus 6 divided by 4 times the quantity of x squared plus 2x minus 15. Go ahead and pause the video and see what you can do with this. Okay, so the numerator factors 5 times the quantity of x minus 3 times x plus 2. The denominator, 4 times the quantity of x plus 5 times x minus 3. That gives us our domain, which is the set of x such that x does not equal negative 5 or 3. But now I notice that there's a factor x minus 3 that divides out in the numerator and denominator. And what that's going to give us is a whole at the point where x is equal to 3. We'll come back to that. The remaining factor in the denominator, x plus 5, gives us a vertical asymptote of x is equal to negative 5. Right? So when factors divide out, there's not an asymptote, there's a whole. Looking at the degree of the numerator, which is 2, and that of the denominator, which is also 2, we can see that we have a horizontal asymptote of y is equal to 5/4. We can see we have a horizontal asymptote of y is equal to 5/4. Now for our x-intercept, we look at the numerator, and it's good to look at the reduced numerator, and so I can see that we have a factor of x plus 2, and so the number that would make that 0 is negative 2. Our x-intercept is negative 2, 0. Our y-intercept is what happens when we evaluate the function at 0. And again, I'm looking at the reduced version of our expression to see that our y-intercept is 0, 1/2. Let me make that a comma. Let's go ahead and put some of this information in our graph. We have our vertical asymptote, x is equal to negative 5, and our horizontal asymptote, y is equal to 5/4, a little bit bigger than 1. And let's see, we've got an x-intercept of negative 2, 0, and then a y-intercept of 0, 1/2. Now what I'd like to know is, does the graph cross the horizontal asymptote? And if it does, then it will be the case that the expression that defines the function will equal the y value of the horizontal asymptote. In this case, I'm going to go for the reduced version, and so we have 5 times the quantity of x plus 2 divided by 4 times the quantity of x plus 5, and we want to set that equal to 5/4 to see if there's a solution. And cross multiplying is going to give me 20 times the quantity of x plus 2 is equal to 20 times the quantity of x plus 5. And if I say divide both sides by 20, then I get x plus 2 is equal to x plus 5. Trying to solve this gives me 2 is equal to 5. And since that doesn't happen, the answer is no. It does not cross the horizontal asymptote. So let's draw our graph. And I'm going to draw a branch that goes through the x and y intercepts and then behaves asymptotically. Remember, a vertical asymptote is never crossed. A horizontal asymptote can be, but won't be in this case. And I almost left out the whole. So remember, there's a whole at x is equal to 3. And so in my graph, what I'm going to do is I'm going to draw a little open circle right there where the graph would go through and x is equal to 3. If we need to, we can use an xy table to figure out the other branch, and we know it exists because the domain is everything except -5 or 3. And we would find that the second branch is in the upper left corner here, and that's our graph. So our x-intercept, y-intercept domain and asymptotes, the result of our analysis, and our graph with the hole at x is equal to 3, where we have r of x is equal to 3x squared minus 3x divided by x squared plus x minus 12. See what you can do with this one. Go ahead and pause the video and crank it out. Okay, so the numerator factors 3x times the quantity of x minus 1. The denominator factors x plus 4 times x minus 3. This is reduced, nothing divides out, and so that gives us our domain, which gives us our vertical asymptotes. Degree of the numerator is 2, the degree of the denominator is 2, so we're looking at the ratio of leading coefficients. We have a horizontal asymptote y equals 3. For the x-intercepts, we're looking for values that make the numerator 0. So we're looking at 0, 0, and 1, 0. For the y-intercept, we're going to evaluate the function at 0. Look, if an x-intercept is 0, 0, so is the y-intercept, right? Now I want to know, does the graph cross the horizontal asymptote? So we set the expression 3x squared minus 3x over x squared minus x minus 12 equal to 3 to see if that has a solution. Clearing the fraction and then taking some steps to solve this thing, I end up with 3x squared minus 3x is equal to 3x squared plus 3x minus 36. 3x squareds go away. Getting the x's on the same side, I get negative 6x is equal to negative 36. This has a solution of x equals 6. And so does this graph cross the horizontal asymptote? The answer is yes, at x equals 6. So let's put this together and get a graph going on here. I'm going to draw the vertical asymptotes, the horizontal asymptote. We're going to plot the x-intercepts, and the y-intercept is one of those as well. Let's see what we get. So I've dashed my lines for x equals -4 and x equals 3, our vertical asymptotes, and our horizontal asymptote, y equals 3. Let's not forget what we just figured out. The graph crosses the horizontal asymptote at x equals 6. And so I'm going to put a dot on the horizontal asymptote where x is equal to 6. And then let's see what we can do. Since the graph does not cross the horizontal asymptote near the origin, in between, I should say, the two vertical asymptotes, and we have those two x-intercepts, I can tell that this graph is going to be asymptotic from the bottom. We're going to cross through an x-intercept, cross through the other x-intercept, and then come back and be asymptotic again. I know that because it's not going to go up, because that would cross the horizontal asymptote in a place that it's not supposed to. As far as the rest of this, test points would be the way to go. Put in x values, you get y values. We're going to find out we have a branch that's in the upper left that is asymptotic above and below. And we have a branch that comes from the upper right, but this one crosses that horizontal asymptote. But here's the deal. It still needs to behave asymptotically as x gets larger. It can't come down and cross the x-axis because we found all the places that occurs. This is going to dip down just a little bit, and then it's going to hug the asymptote for all eternity. So this is the graph that we were after. We're so proud of our intercepts, asymptotes, and domain. We're going to circle those, and there we are. Next we have x cubed plus 2x squared plus x minus 2 over x squared minus 1. Since the denominator factors x plus 1 times x minus 1, we have the domain, the set of x such that x does not equal plus or minus 1. Here's the deal, the numerator doesn't factor. That it doesn't factor means nothing's going to reduce, so we do have vertical asymptotes of x equals 1 and x equals -1. As far as the oblique or slant asymptote, the degree of the numerator is 3, the degree of the denominator is 2, and so we need to use long division. Let's see how that's going to go down here. And because I'm only concerned with the quotient, I stopped it when I found that the quotient is x plus 2, so the slant or oblique asymptote is y equals x plus 2. The x-intercept is going to be a little bit tricky here, so we'll come back to that. The y-intercept is, of course, where x is equal to 0, and so 0, 2 in this case. Let's draw as much of this as we can. Vertical asymptotes, our slant or oblique asymptote, then we'll plot our y-intercept. At this point, I'd like to know, I can see that the y-intercept is on the slant asymptote. I'd like to know if the graph crosses the slant asymptote anywhere else. So, doing the thing that we keep doing, I'm going to set the expression equal to the slant asymptote's expression and see if there's a solution. A solution other than 0, that is. So, x cubed plus 2x squared plus x minus 2 over x squared minus 1 is equal to x plus 2. We're going to clear the fraction, and then we're going to solve this thing. After doing so, we see that x equals 0 is the only such solution, and so we don't have anything else going on there. Now, this is the worst of all possible worlds. The numerator doesn't factor. What I would do if I could, and what I tried, was treat it like a polynomial, make a list of possible rational zeros, in this case plus or minus 1 or 2, and then use synthetic division to hope we have a 0. Didn't work. We have no rational solutions. So what we end up having to do is pick test points, just to kind of see what the nature of this expression is. If I pick a test point that's, say, -10 or -5, as it turns out, I'm going to get a negative answer. If I pick a test point of, say, 5 or 10, I'm going to get what turns out to be an increasingly positive answer. As far as in between the two asymptotes, I might pick, I don't know, -3/4 and +3/4 to see what's going on there. After doing all of that and using the positive and negative outputs that we get for the expression, we're going to end up with, let me clean this up a little bit, a branch in the bottom left that behaves asymptotically, a branch in the upper right that behaves asymptotically, and then a wiggle in the middle that goes from the top left portion to the bottom right portion in between those two vertical asymptotes. The x-intercept is at about 0.70, 0.7. That's something that we would obtain using, say, calculus techniques. What I do know is that from using test points, I can figure out where the function is positive or where it's negative. We can be so proud of our x-intercepts, our y-intercept, our asymptotes in the domain. The x-intercept, I'm going to leave it as irrational because I wouldn't expect you to actually come up with that value. We kind of just don't have the tools just yet. But this is our graph. Now, let's wrap up all of this stuff. To analyze rational functions, which are generally of a form r of x is equal to a polynomial numerator and a polynomial denominator, we first are going to look at the domain. The domain is the set of x such that the denominator does not equal 0. Once we've done that, we reduce the rational function if we possibly can. And after reducing, then we can figure out the vertical asymptotes. Those are numbers from the denominator, the factors of which do not end up dividing out. After reducing, we look for the ratio of degrees. We look at the degree of the numerator and the degree of the denominator. If the degree of the denominator is smaller than the degree of the numerator, then we have a horizontal asymptote of y equals 0. If the degrees match in the numerator and denominator, we have a horizontal asymptote, y equals a ratio of leading coefficients. If the degree of the numerator is bigger than the degree of the denominator, then we have an oblique or a slant asymptote, depending on what you want to call it, and it's going to be y equals the quotient from long division. Then we set the numerator equal to 0 to figure out the x-intercept, or the intercepts I should say. We evaluate the function at 0 to find the y-intercept. There's only one of those ever, sometimes none, but never 2 or 3. And then finally, we want to know, does the function cross either the horizontal asymptote or the slant or oblique asymptote? It'll never cross the vertical asymptote, but as you saw, sometimes it can cross the other asymptotes. We put all this together, and then, if necessary, we plot points to see what the nature of the graph is in certain areas. The domain, the vertical asymptote or asymptotes, the horizontal or slant asymptote, and the intercepts, x and y, are all part of analyzing rational functions, and they all get represented in the graphs thereof.